Hi everyone, let's talk about LTE architecture in this lecture. LTE, as you all know, it's a long-term evolution which is based on GSM and UMTS standards. As you see in this slide, you see various network elements, and I'm going to explain you from the next slide each and every network element in this slide and how your data packets travel. Suppose you request a link, suppose CNN.com, how the data packet travels from the internet, from the CNN.com server through all the gateways, the P gateway, the S gateway, E node B to your device, how the data packet travels, takes its way from internet to your UE through all the gateways. Let's start the lecture. Uh, Suppose you are traveling, you have your device, and you are traveling from one city to the other city. Suppose you are traveling from, suppose a city Chicago, and you are going to Indianapolis. So, and you have your device in your car and you're requesting, suppose, a CNN.com link. So, all the packets from the internet from the CNN server have to travel from the internet CNN server to your device. So, as your device, your car moves mm, from Chicago or within Chicago, it has to move around all the towers, the antennas, right? So as it travels from one antenna to other antenna, one tower to our other tower, we call in the LTE architecture these towers E node base. E node base are enhanced node base stations. As the car travels, as the device travels from one E node B to the other E node B, your data packets from the CNN server, it has to send all the packets to each E node B and then to the device. So as the car moves from one E node B to the other E node B, because of the mobility, the IP address always changes. So, but the internet has to send its data packet to a particular address, particular IP address. Uh, so, to resolve this logic, we introduce a gateway called P gateway, which is packet gateway. So internet first when you request CNN.com or any other link, it sends the packets to the P gateway because the P gateway is assigned a particular IP address. Uh, IP address here, IP address is homed at P gateway. So all the internet packets from your internet from your CNN.com are sent to your this particular IP address P gateway, and from the P gateway, your data packets travel to your inode B. Suppose it's inode B1 to your device. As it moves to your car moves to your device moves to inode B2, from P gateway to inode B2 to your tower 2 to your device. As it moves from 2 to 3, tower 3, from your P gateway to tower 3 to your device in the car. So your data packets travel from the internet, from the server, CNN server, to your packet gateway, which has your IP address. Because internet, the server has to send your data packets to a particular address, IP address, which is on P gateway. Your IP address is homed at P gateway, and to the towers, to the eNode Bs, to the device. Here I can give you one example. Suppose you take your mobile device and do what is my proxy.com and you get an IP address. That's the IP address here. The IP address which you see in what is my proxy in your device, right? That's the IP address here. That's the IP address which the internet sees and sends your data packets to the P gateway. And here, as your device travels from one e node B to the other e node B, there's a lot of mobility, and there's a lot of traffic onto the P gateway. To avoid this, we introduce one more gateway which is called S gateway, which is serving gateway. Serving gateway, the main function is it's a anchoring of your mobility from one E node B to the other E node B, and which is not visible to the P gateway. So all your data packets from the internet to the gateway are moved to S gateway and then to your enode base. So here, let's remove all this. Uh, so all your data packets are moved from P gateway to the S gateway, and all your mobility is managed by your S gateway. So your data packets, as car travels from one enode B to the other enode B. Suppose the car is at tower 1 enode B1, your data packet from internet travels to P gateway to S gateway to 1, and then car travels to 2, then the P gateway to S gateway to 2, then to 3. So as the car moves from one tower, one enode B to the other enode B, the data packets move uh, from P gateway to S gateway to the particular enode B, and then to the device. Uh, suppose the car moves from one enode B to the other enode B, and some of the packets are still in enode B1, and then they have to move to the enode B2, the remaining packets. So it uses an interface called X2. X2 is the interface between the enode Bs to move the remaining data packets from the previous enode B to the next enode B. And next, we'll talk about a network element called HSS, which is home subscriber subsystem. Suppose you have your Netflix account, your Prime account. So you pay a monthly bill and you have a subscription. Uh, in the same way, the SIM in the device, you pay your network operator your monthly bill, and sub, you're subscribed to that account. So HSS is nothing but a database which has all the customer details, which takes care of authentication, identity of the subscriber. uh, it has all the details. The database which has the identity, authentication, subscription of the subscriber. And let's talk about the other network element here, which is mobile management entity. Just like MME, just like S gateway, which is the anchoring of the mobility from one enode B to the other enode B, MME is does the same thing. Uh, MME checks the database HSS to find out the subscriber details, the customer details, whether he has his billing done, whether the authentication is good. Like it checks the authentication, its username, like a username or password, or everything in the database about the customer subscription, and tells enodebs and S gateways that yeah, this subscriber is good and you can send the data packets. He is good to browse the data. He's good to browse the internet. So MME talks to enodebs through S1 MME. The interface is called S1 MME, and MME talks to S gateway, and the interface is S11, and S gateway to enode B, it's S1U. So MME talks to HSS to check the authentication, to check the identity, and in turn it's talked to enode B and S gateway through S11 interface and S1 MME interface to the enode B to tell the respective gateways to respective enode Bs that the subscription is good and you can send the data packets. This is all the basic level of the LTE architecture. As we go to the next lectures, I'll explain you all the call flows, what happens between the device and the enode B, between the MME and the E node B, S gateway, P gateway, all the barriers which are created, all the tunnels which are created, but all that comes in the next slide. This is the basic overview of the LTE architecture. So your S gate, your data packets are sent from your internet to P gateway, which is called SGI interface, and your P gateway sends your data packets to S gateway, which is SY interface, and your data packets are traveled from S gateway to each eNode B. eNode B1 if the car is at 1, if eNode B2 if your device is at 2, and the interface is S1U, and the data packets are traveled from your eNode B to your device through the this is called the LTE UU interface, which is the radio interface. It's the air interface. So we have a complete different lecture on air interface. So this is how the data packets travel from your internet to P gateway to S gateway to eNode B to your device. You must have observed here, I used solid lines and also I used dotted lines. Solid lines you see for S5, S1U, X2 and LTE, right? There is, and so the dotted lines for S11 between MME and S gateway, S1 MME between MME and eNode B, and this is X6A between HSS and MME, and we have also dotted line S5. S5 has both dotted and the solid lines. So what is a solid line and what is a dotted line? Solid line here, it's nothing but the user plane, UP, user plane. User plane is nothing but where your actual data travel happens. You request a link cnn.com and the server sends actual data packets, and the route it takes, suppose here from the internet to the P gateway to S gateway to eNode B to your device is actual your data packet travel, and that's your user plane. And here dotted line is control plane, is your control plane. Control plane is there is no actual data travel, but here it's all signaling takes place. Signaling is nothing but MME checks with HSS, signals HSS, talks to HSS to check the authentication. In turn, it talks to it talks to eNode B and it talks to S gateway to just let them know that the subscription is good, that it's just signaling. There is no actual data packet. So all the signaling part is the control plane. All the actual data travel is your user plane. So CP is control plane, UP is user plane, actual data travel, and signaling is your CP. So I hope you understood the difference between UP and CP, control plane and the user plane, and how the data packet travels from internet all the way to your device using different interfaces, UP interfaces, user plane interfaces, SY, S1U, and then LTE, UU, the air interface, and then the signaling part, S6A, S11, S1MME, and SY. Suppose your device now travels from Chicago to, it goes to another city. Suppose now your device is in Indianapolis. Here we take the example where the car is all the way, it moved from Chicago to Indianapolis, and it changed its, and it has its own eNode Bs here, its own towers in this area. Suppose we call it tower 4, tower 5, tower 6, right? And your data packets, and here it has its own S gateway again, because it's a different city. I'm taking an example where the two cities or the two areas have the same PGW, but now the S gateway changed. So your data packets travel from internet to P gateway to S gateway. Suppose call it S gateway 2 and this one S gateway 1, and your data packet comes through not be 4 or 5 or 6 based on where your car is, your device is. And Indianapolis, when it moves to a different area, let's call it has its own MME2. So suppose call it MME1 in Chicago, MME2 here. So the same, it's a same function what we have seen before. MME2 enode base, it's S1 MME again. It talks, it signals the signaling control plane, and S1 to S gateway to S11, and again S gateway 2 to all the enode base here S1U, and P gateway to SGW2 is your SY. So as your device moves from one city to the other city, it changes its S gateway and it has its own MME, and the function is same. MME takes care of all the control plane signals. It takes care of the authentication. Again here HSS. I forgot the HSS part. S6A. It MME takes care of all your authentication identity, and it lets SGW and we know about the movement of the device from one tower, from one enode B to the other enode B, and your S gateway, P gateway, the same user plane again. Internet packet travels from P gateway to S gateway to respective enode Bs 4, 5, 6, and reaches the device. And you one MME talks to the other MME, and there is an interface for this from one MME to the other MME, and this one is S10. One MME talks to the other MME through the signaling the signaling protocol, which is S10 through the S10 interface control plane. This is the basic architecture of the LTE. We can talk more on the LTE architecture, all the call flows. We can go deep into the each interface from the next class, next lecture. But this is the basic uh, explanation of LTE architecture, to know about all the interfaces, about all the network elements, about the user plane, about the control plane. And now I want to tell you what's EPC. EPC is nothing but evolved packet core. Your LTE core is called EPC, evolved packet core, and that consists of from your PGW2, your SGW, without including your towers, without including enode Bs, all your MME, all your HSS, SGW, PGW, all the way till here, without including the enode base, it's EPC, which is evolved packet core. And your enode base, all the set of enode base here and all the set of enode base here are called EUTRAN, which is enhanced node base stations. So all your enode base are called EUTRAN, enhanced node base stations, and EPC is all the core, LTE core, which is evolved packet core. Um, so evolved packet core and is a and your EUTRAN combining together with your device. It's a complete LTE architecture. Yeah, this is the LTE architecture. Let's go back and look at the block diagram again here. So yeah, this is the block diagram of the LTE architecture. As I explained you before, your internet packet, when user UE device requests a link, suppose CNN.com, the packets come from internet to your P gateway, to your S gateway, to internet, all the way to UE. The request comes here, and all the this is the user plane, and all your signaling takes place. It's taken by MME, and there's also a signaling here between your sorry between your SGW and PGW, SY, and S10 is from one MME to the other MME, S6A, S11, S1 MME, all the control plane part and the signaling part. I want to introduce a little bit on the 5G here. It's simple. Suppose let's see this slide. So as you see on the top, we have LTE architecture, and the bottom we have 5G architecture. So if you see on the top on the LTE architecture, here, as I explained before, the signaling part, the control plane, and the actual data packet travel, your user plane, are combined together in your LTE. As you see here, your SY uh, has your both user plane and control plane, and your MME S11, S1 MME, S6A, everything, the user plane and control plane are combined in your LTE. But on the 5G uses architecture, it's a cups architecture, control plane and control plane, user plane separation. Here your control plane and user plane is separated. If you see here, your data packet in the 5G travels from your internet to UPF to RAN to UE, and there is no control plane here. It's just a solid line. Your data, just the data packet travel, and that's all the user plane. This is all the UP. It's not combined with any CP. But on the upper part, when you see your AMF, your UDM, your SMF, your PCF, it's all the signaling, all the dotted lines. So on the up, it's completely separated. On the upper part, it's a CP control plane, and the lower part, it's completely UP. So this is the CUPS architecture, the basic introduction of the 5G CUPS architecture. It's a basic control plane and user plane separation. All the upper part, your AMF is same as your MME in the LTE. Your UDM AUSF is like HSS. SMF is just like your MME, HGW, PGW. Your UPF is same as your SGW, PGW. It's the same thing, different abbreviations. But here completely the control plane and the user plane is separated in the 5G, but on the LTE it's combined. Here, don't worry about the S8. S8 is the interface between SGW and PGW in the roaming scenarios. Roaming scenario is nothing but, as I told you, right, in the previous slide, the device moved from Chicago to Indianapolis, but it's the scenario where device moves from one country to completely to the other country. It's a completely different scenario. It's a roaming scenario. But I'll explain you the roaming scenario in the next lecture. But I hope the basic core LTE architecture and the introduction to the 5G CUPS architecture is clear from this lecture. If you want to see more on the abbreviations, I have some abbreviations here. The basic, suppose in the LTE part, IMEI is called PEI in 5G. MISDN MSISDN is called GPSI in 5G. IMSI on LTE is called SUPI or SUCI in 5G. MME AMF in 5G. SGW plus PGW. SGW PGW, it's a SMF plus UPF. HSS is called UDM. OCS is CHF. PCRF is PCF. Dedicated barrier in LTE is called GBR flow, which is guaranteed bitrate flow. And PDN connection is called PDU session. PDN is DN, and APN is called DNN in 5G. I hope I'm clear with the basic LTE architecture and the introduction to the CUPS 5G, your control plane and user plane separation. Thank you. I'll explain more on the call flows from the next lectures.